Hi everyone, I'm Hilal Maiti from IIT Kharagpur and I'll be presenting my topic on adapting AI into low power testing, which was accepted in our academic research track. And I'd like to thank my co-author Shantanu Chattopadhyay for his valuable contribution into this work. Uh, Advancements in data science has enabled various domains to achieve unparalleled performance and efficiency. Different domains of artificial intelligence held the center of interest for researchers, academicians, and industrial practitioners. Be it weather forecasting system, be it fraud detection system, or even be it drug discovery practices. AI has proved to be a powerful tool in each such domains. Inspired with this, we aim to find out potential techniques in low power testing domain that may inherently be benefited with standalone or integrated version of AI-based frameworks. First, we'll discuss the objective, then we'll move forward to a previous class-based reordering approach. Then we'll discuss about our proposed reordering techniques. Then we'll explore how that proposed approach has a major flaw or issue into it, and then how we are using an AI-based technique to resolve that particular issue. After that, we'll discuss the structure and performance of the AI model. Finally, we'll discuss our framework along with the experimental results to validate our work. Then we'll conclude the overall presentation. So our objective is basically the test patterns generated by the ITPG. We have to reorder them in a way that before applying those patterns into the circuit under test, the overall power dissipation should be minimized. So suppose the patterns are P1, P2, P3. If I apply first P1, then P2, then P3, the power dissipation is coming out to be 35 milliwatt. But if we reorder them like this, first P2, then P3, then P1, then power is getting reduced to a milliwatt. So clearly for n test patterns, there will be a total of n factorial different ways to rearrange them. And we have among that particular n factorial ways, we have to find out one such order that will result in minimum power dissipation. So what is the order of pattern application which will result in minimum power dissipation? This is our goal, and the goal is to find how AI can be utilized to solve this reordering problem more efficiently. So power estimation is done by using this formula. Switching activity at the gate nodes causes the capacitive loads to charge or discharge, as you know. So this is the major source of dynamic power dissipation. So that is why we are, for each of the node, we are multiplying the switching activity along with the fan out value, and for we are repeating this for each of the node in the circuit under test, and finally we are summing those products up to get our desired power estimation. And this is done for all the shift, launch, and capture cycle. So the previous work is class-based reordering, where the pattern P and Q are being inserted in the scan chain. The scan chain was originally initialized with all 0. Then we are inserting the least significant bit of the first pattern P0, and the bits are inserted serially bit by bit. After the P is inserted, we are getting the response R, and then again we are inserting the Q bit by bit serially, and we are getting the response of the second pattern S. And this transition keeps repeating till the end of the scan. So there is this particular transition R3 and Q0. Okay, so as you can see that this keeps repeating till the end of the scan chain, and if R3 and Q0 are complementary in nature, it causes the power to surge to a high amount. So in order to avoid this particular situation, the proposed approach has been that classify all the patterns into these 4 categories: class 00, 01, 10, and 11. So class 10 is nothing but the least significant bit of the pattern is 1, and least significant bit of the response is 0. So those kind of patterns are classified as class 10. So next you can see that all the classes are arranged in this particular manner. All the class 00 is merged together. Then we are applying all the class 11. Then after that we pick one class 01, and next we pick another class 10, and we keep this pattern alternate in alternating manner. So this ensures that R3 and key 0 are like not complementary to each other. So by rearranging in this manner, they try to reduce the overall power distribution. Next, we have mapped our problem into a traveling salesman problem. So we have formulated a directed graph where the nodes are present. Nodes are nothing but the test patterns, and the connection between the nodes are the edges. The edge values are the power distribution between the patterns. So for example, if I want to go from 010 to 110, then I can see that the overall power distribution is 9, but in the reverse direction the power distribution is 11. The modified greedy approach that we have used is the Prince inspired forming of the spanning tree. Suppose this 1 2 3 are three nodes that already has formed by the Prim's algorithm, and next it is searching for 4, the next closest node. So what it will do is it will go back to 2, then go back to 1, and then connect to 4, because 1 is closest to 4. So this causes the patterns to repeat. In order to avoid that, we just directly reached out to 4 from the latest node, which is 3. So we can see that the difference in power, and we have solved our repetition in pattern, and also we can see that that causes the power to reduce as well. Prim's algorithm originally fails for the directed graph, but it works in our case pretty well. Why? Because our graph is always fully connected in nature, and all the edges are bidirected, so it can go towards both the directions. So the algorithm never reaches an isolated node where from where it does not have a way to go out to. So it will always have a way to reach out to the uncovered vertices or nodes. So next we are applying the Kernighan-Lin approach. Uh, we'll also refer as scale. So the modified version of it, we are applying it on our reordering problem. So suppose we have 6 test patterns P1 to P6, and we are picking 2 random patterns P2 and P5 and these two are selected for swap check. Swap check is nothing but we are taking input a pair of patterns and we are swapping them, like the positions of them are swapped, and we are checking if the swap has caused a reduction in overall power distribution or not. If the swap check comes out to be true, then we'll consider that the swap has reduced the overall power distribution, and vice versa. So here P2 and P5 has returned a swap check value of true. So we have swapped them. So here is P5, here is P2, and locked them into their corresponding position. Then we'll move forward to P1 and P4. P1 and P4 provided us a swap check value of false. So we did not swap them, but we still locked them into their position, and we keep locking each of the selected pairs until all the pairs are locked like this. Upon reaching this particular state where all the patterns are locked into their position, we'll check that if the overall power has been reduced, and if it has reduced, then we'll unlock all the patterns like this and repeat it in the next iteration. So we'll move forward to the another iteration. Otherwise, we'll terminate the program and declare this particular order as the final solution. STM is nothing but the patterns which are uh, like arranged like this. It is basically a matrix. It provides us information about the switching activity. So it has all possible switching activity values for the provided ATPG generated patterns. So suppose if I want to check for P2 to P3 transition, so P2 to P3 switching activity is S23, and if we have n such test patterns, we'll have n square minus n simulations running to calculate the overall STM values. So this introduces a runtime overhead for circuits with large inputs. So when n is large, the STM estimation time goes pretty high. So here we are utilizing our AI based technique to get rid of this problem. The idea is to avoid the repeated simulation to overcome the runtime issue. A deep neural network is trained to predict the output of the power estimation function when two patterns are provided as input. We can replace the repeated simulation with a predictive model. Simulation cannot be entirely eliminated, as we still need it for preparing the database to train the deep neural network. So here is the database that we have prepared with the actual power estimation function. So these are the pair of patterns, and for this particular pair of patterns the power is this, and we are using this database to train the DNN. And now I'll ask P2 and P3 to go into the DNN, and the DNN will tell that the power distribution between P2 and P3 is S32, like that. So there is one other metric called weighted transition metric. It is calculated like this. So why it is useful for our case? WTM is usually used for having an estimate of transition occurring in the scan chain due to specific pair of patterns. WTM cannot be an accurate measure of overall power distribution. We have utilized WTM as an input feature to train the DNN. So it trains the overall network better. This helps the model to learn better, as the goal of the model is to predict the overall power distribution. So our network structure looks like this. So generally we have a pair of test patterns like this, and for this particular pair of test patterns we will have a WTM value. Note that the pattern values are categorical in nature, so it is basically binary patterns. So either it will be 0 or 1. So these are two categories, but the WTM value will be continuous in nature. It can have any integer values possible. So for the categorical values we'll do one hot encoding, and for the continuous data we will normalize it, and the one hot encoded values will go into the embedding layer. The output of the embedding layer go into the linear fully connected layers. The normalized values will also go into the fully connected layers, and the fully connected layers will give us the desired output or the prediction, and we'll compare that with the target data, which is the power distribution calculated by the simulator, and here we'll have the error function of our network. So why we use DNN? So we have a tabular data to start with, so we have to train our network with our tabular data. Popular techniques like XGBoost or random forest works well on tabular data, but higher number of circuit inputs leads to higher cardinality. Cardinality is nothing but the number of independent variables in our dataset, and the DNN works better on data with high cardinality. Okay, as well as majority of our input features are categorical in nature. If you remember, the WTM is the only continuous data, and the rest of the input features are all categorical data, and categorical data goes through one hot encoding. One hot encoded features are highly dimensional and sparse in nature, and DNN offers embedding layers that reduces the dimensionality without extensive feature engineering. So size of the embedding matrix is decided by this formula, and the embedding technique is widely used in NLP, and we have drawn our inspiration from that. And the linear fully connected layer structure changes from circuit to circuit. Usually we have 2 to 4 hidden layers, and the number of neurons in each layer can vary from 20 to 600. We have obtained an average accuracy of 98.920 for S5378, and average if you average it for all the circuits, we can see that the average accuracy is 99.454, which is state of the art accuracy. And if you see the worst accuracy on the test data, so we are calculating on the test data, so the worst accuracy is 96.958, which is still good. And the parameters that we have used as discussed here, the optimizer is Adam, the train validation test split is 7:3:2, the batch size is 128, and we have used a dynamic learning rate. The learning rate is picked by plotting the loss function against various learning rate values, and each hidden layer may use a different learning rate value. So the overall framework looks like this. We'll start with generating a set of test pattern using any ATPG and some other random pattern pairs. So these pattern pairs will be run through the power estimator and as well as WTM estimator. So for each of the pattern pair will have a WTM value and one power value, and these will be stacked up against each other to create the database. This database will be used to train the DNN, and the DNN will predict all the power values to, and it will help us to formulate the STM much faster than before, because we are using the predictive system instead of the simulation based technique. Compose the directed graph. The ATPG generated patterns will be utilized to form the nodes of the graph. So on the graph we'll run the Prim's algorithm and extract various spanning trees or orders. And the ATPG generated patterns will be also shuffled 100 times to get 100 random orders, and these two obtained orders will be run through KL, and KL will utilize the graph as well, and KL will return us the optimized order and will end our terminate our framework here. And if you observe that the results are very promising. The blue bar here is the class-based reduction, green bar here is Prim's algorithm reduction, and KL algorithm reduction is the yellow bar. So for each of the circuit you can see that the KL reduction is much more than the class-based reduction. So these reductions are with respect to ATPG generated order. If you see the quality of the DNN, this was the framework without the DNN, so we have not utilized the DNN to get this result. Now we'll utilize the DNN to get the similar result, and we have seen that the DNN based framework was achieving an accuracy of almost 97% in average. So these errors are compared with the framework without the DNN, means this one. So we can achieve this result with 97% accuracy with the help of the DNN based framework. And if you see that the speed of the DNN based framework multiple times faster than the simulation based ones, 162 times to be exact. So this y-axis of this plot is plotted in log scale. So you can see that the DNN based framework is multiple times faster than the simulation based framework. To conclude this work, the simulation based reordering framework can reduce 37.73% of the overall power generated by the ATPG, and the DNN based reordering framework can achieve the above result with 97% accuracy, but with 162 times more speed. The work reinforces the wide possibilities of AI based efficient VLSI testing techniques. The proposed DNN based technique cannot replace the circuit simulation entirely, but can replace the repeated cost based estimation and simulation. Here are the references. Thank you everyone.